And I'm going to just go here for a second. It's 9 lessons or 9 topics, but sometimes they take multiple days or we need days of practice. So I would say if you're looking at the front here, we'll probably do a quiz after day 3. Okay. Now this might take, like this is today. I think we might be able to get through most of this tomorrow, but then this is definitely going to take a couple days. Okay. So you can probably expect a quiz maybe next Thursday or next Wednesday. Like I don't know, because it's about pacing, right? But if you miss a day, you got to make sure you kind of get to the notes and try to figure out the calculator stuff. You can always come in and borrow a calculator if you need to, but then we just have to be really responsible with those items. The other thing I noticed, if you guys can help me because you're more mature adults, I'm hoping, if you see writing on the calculators, will you please let me know as soon as possible so I can clean them up? It really bothers me that kids just think they can write on it. I know they think they're just doodling, but you're doodling on a piece of equipment. It's fine. Okay, here we go. So this is this. Now, if you turn the page to the back of the cover sheet, and I hope this copied okay on the orangey paper. Did it copy okay? This is just, I wanted to give you guys just an overall idea of visual things we can do for statistics, and that's why this is going to take a bit of time, is we have to learn how to make some of these, some by hand, some in our Google spreadsheets. Then we also are going to be doing number crunching, that's summary statistics, and then what those things tell us. So these individual pieces, numbers, give us one piece of information, and we compare it to the graph of the data, and then we can draw some conclusions or observations about that data, okay? So the one thing I wanted to do up here was kind of try to show you that we have quantitative displays, and then we have categorical displays. So once again, things like a pie chart can't do the heights, our heights, right? Our heights would go in something like a histogram. However, if we're going to talk about our pets, we're going to be over on the pie chart side. And there definitely are like more displays than this. There's like a 1,000 different ways to display data, but there are some that become more helpful in being able to describe and make decisions. And so we're going to get to some of them, but we don't get to all. We also, you have done two-way tables before back in Algebra 1. It's just a nice way to compare two different ideas that are categorical, okay? And we work with percents a lot on this side of our data in the categorical data. Okay, so turn the page. Beep. Okay, page 3 is where we write our first words down. Oh my gosh, there's words. All right, so once again, some helpful vocabulary, where we're going. Let me just get to this page, thank you. Okay, so we played with Barry Bonds and Babe Ruth. And although we had 2 dudes, we were playing with data that has only one attribute or characteristic. Okay? Home runs is one attribute. So we call that univariate data. UNI and then variate. Univariate. All right. Then there will be times that we make scatter plots, and this is kind of more of what you do in science class when you're like comparing temperature to like something like time and temperature, like you're melting something or boiling something, you're seeing what's happening over time. Grab a note packet from there and then grab your calculator. So when we are comparing 2 variables, that's going to be displayed on a scatter plot often. That's called bivariate data. And that's when we can do regression lines, okay? Oh, yay. And I should be able to just refresh this and come here. Fabulous. Thanks, Maddie. Okay. So there are some examples over here for those two, and this is where we spend most of our time. We actually, this unit, so unit 2 is all univariate data. All univariate. We'll do a small unit after this with bivariate data. So this is going to be linear regressions. It's pretty short. And that's going to be unit 3. And that's when we're trying to see if there's a relationship, a correlation, an association between two variables. Once again, we can't do quite cause and effect, but we can see if there's a pattern. Okay. And then the last thing is actually just kind of what often happens in the real world, this idea of multivariate statistics. All right. And that's because there's usually more than one variable involved. So, for example, things that have to do with your health, a statistician or a dietitian might collect data on all sorts of things: your cholesterol, your blood pressure, sugar levels, what are your habits, what do you eat, how do you exercise, family history. All of those variables go in. Sometimes we can actually make formulas with multiple variables like that. It really can be done, but we're not going to be doing that, okay, at this level. But that does exist, that multivariate. And then this is kind of a repeat from the previous page. When we're playing with univariate data, we can do these stem and leaf plots, histograms, dot plots, box plots, and those ones are all quantitative and where we spend the majority of the unit. And then we do a little bit of categorical stuff at the end. And then I mentioned this yesterday, when we're making plots, you want to make sure that you're being as neat as possible. If you are someone that likes to use a straight edge, then just always grab one. They're right by the calculators. And then this is like a memory tool that doesn't fit perfectly. Title, tick, tick, label, 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 because sometimes you don't need 3 labels and you might not even have 2 axes. But it's there to help remind you, am I doing all the stuff I need to do to make this a complete graph? Cool? Cool. Turn the page. Beep. All right. And so this is going to be our lesson on stem and leaf plots. Those of you that got to make those on the first day, you have a little bit of a leg up. And we start off with an against all odds video. You might remember, you might not remember. One of the very first videos we saw from Against All Odds talked about outfitting our soldiers with their physical equipment that goes on their body. And so this is kind of that process of collecting data to then help make sure that our uniforms and other protective equipment actually fit our service people correctly so they are safe. So a couple things they're going to talk about. They're going to talk about variables that are taken on the soldiers. They're going to talk about the shapes of distribution. So that's a big idea when we're describing data. We talk about the shape of distribution. This one's about foot length. Center of distribution, so shape and center. And center, those are 2 big ideas. Then they're going to change over to talking about Toyota and cars, and they're going to talk about fuel economy or miles per gallon. And then that's going to show another idea with stem plots. And there's going to be a back-to-back stem plot displayed. So this is an opportunity to once again see all the different types of stem plots that are out there. And there's going to be an additional kind of 2 ideas that we add in that we didn't get to use with Barry Bonds and Babe Ruth. So let me pull that video up. And we will have movie time. Movie time. You guys know Wayne's World? Do you know Wayne's World? Wayne's World, Wayne's World, party time, excellent. All right, sorry. I've lost my mind. Okay, here we go. Let's get our video up and running. Here we go. We're going to play.
Funding for Hello, I'm Pardis Sabeti, and this is Against All Odds, where we make statistics count. Statistics is all about the data. And frankly, it's easy to feel overwhelmed by an avalanche of numbers if we don't figure out good ways to organize it all. One of the best places to start is with a picture. You've seen informative pictures like these before: pie charts, bar graphs. Visualizing data like this can be a good first step towards organizing it and understanding it. And it provides a framework to contextualize a single number you might encounter. For instance, my friend told me her new baby weighed in at 7 pounds and 8 ounces. I'm not a baby expert, but I can use these graphs to get a sense of where on the continuum from tiny to gigantic this one baby fits in. Looks like he's right about in the middle. There are a variety of ways to visualize raw numbers and tons of real-world data sets to work with. Let's step into the Army's boots for a moment to see the data it collected to help outfit each and every soldier with the right size uniform and gear. Since the Civil War, the Army has kept tabs on the size of its soldiers, tracking changes over the decades. Throughout the 1900s, Americans grew taller due to better nutrition and medical care. Once that countrywide growth spurt had maxed out, the Army thought it had a handle on its soldiers' dimensions. But in 2003, as Army leaders started outfitting soldiers for Operation Iraqi Freedom, they noticed they had a gear shortage on their hands.
There were some indications that we didn't have the right numbers of sizes of equipment. And it was critical equipment, because back then, you might remember, we were talking about dirty bombs and that sort of thing. So we needed to make sure they had the right chemical equipment and ballistic equipment. And we found that we did not have that in the correct numbers of the correct sizes. And so that was like a, ding, 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 bell kind of a situation, because we had had them in the past.
And this was a clue to us that our database was out of date. Now, we'd been tracking the increase in body size in civilians, but you don't necessarily expect the same increase in body size in the military because we have weight for height standards.
Stockpiles hadn't been adjusted to reflect the changing shape of today's all-volunteer Army. It was time to call in the anthropometric team. They're the scientists who conduct the survey to update the size database. They would figure out how big today's soldiers are and how big the equipment designed for them needs to be. Researchers traveled the country to multiple bases and randomly sampled almost 12,000 active duty soldiers, National Guard, and Reserve members. The goal was to learn the complete size range of today's soldiers and how common each size is.
Each person, we took 94 dimensions. That's, heights, weights, breadths, depths, those kinds of dimensions, and 3 scans, one of the whole body, one of the head and face, and one of the foot. But there are a variety of ways in which you can gather that data, and you use the right tool for the right job, so to speak. Sometimes when you were just doing, for example, circumferences, they would just use a regular tape measure.
The measuring team confirmed that soldiers are bigger now than they had been in the past. From 1966 to 1988, they had already seen a weight increase due to more muscular physiques, thanks to the popularization of weight training. Now they were seeing an increase in body circumferences related to where body fat is stored. As part of our national obesity epidemic, soldiers are bulking up right along with their civilian counterparts. Whatever a soldier's size, it's crucial that his gear fits well so that he can do his job and be protected. The survey's precise measurements become a valuable resource for designers working on the next generation of everything from body armor and boots to workstations and vehicles. This was the first big survey that created 3D scans of each soldier that can be used when designing a new cockpit, for instance.
To do that without physically creating a cockpit model and putting people in it, which is very costly and time-consuming, what you would do is you would take the dimensions of the cockpit, put it into a virtual space on the computer. Then you would need a human of particular dimensions that you want to fit to also put virtually in that space, and then to go through a series of tasks. Now, the dimensions of that digital human have to reflect the dimensions of the users.
And with a better sense of the most frequently found dimensions nowadays, the Army knows which sizes to keep well stocked and which sizes are rare enough that it's cheaper to custom order them. But saving taxpayer dollars isn't the only concern.
It's a particular underlying consideration that we who develop and design equipment always have in the back of our minds. It's soldiers' lives, it's soldiers' lives, it's soldiers' lives.
Here's the foot measurement data in centimeters for 30 of the soldiers. When you see a bunch of unorganized numbers, it's hard to tell if they have any rhyme or reason. Let's organize these data into a stem plot to get a better sense of how widely foot size varied. First, using software or a calculator, we can sort them into numerical order, which already gives us a little bit better idea of what's going on. Now, let's separate each measurement into a stem and a leaf. The stem is the first digits, and the leaf is the final digit. Line up the stems in order vertically. Then fill in the leaves on the appropriate stems. In this case, the final digit is the tenths of a centimeter. Always include all possible stems in your data range, even those that don't have leaves to go with them. The final step is to organize the leaves in numerical order. Displayed as a stem plot, we can see the overall pattern of our data. The 26 centimeter values are the most common, and values on either side of that single peak are less common. In this case, the peak looks to be around the center of the distribution, which we can calculate. There are 30 measurements. Half of 30 is 15. Counting up 15 observations, starting at the smallest, lands us at 26.8. So that's roughly the center, or midpoint. A stem plot also lets you see at a glance how spread out the distribution is. The data points range from the smallest at 24.6 centimeters to the largest at 32.8 centimeters. Check out the overall shape too. For the most part, the stem plot looks pretty symmetric, except for that value out there at 32.8. An individual measurement like this one that falls outside the overall pattern of the data is called an outlier. It's important to try to figure out what's going on when you see an outlier. Is it a mistake? Did someone just type the digits in wrong? Did someone measure in the wrong units or deliberately add a joke number? Sometimes outliers are in fact real data, but it's good to take a second look to make sure. Stem plots work best with data sets that are relatively small. You wouldn't want to make a stem plot of foot measurements for all 12,000 soldiers who were sized up. It would be too unwieldy to help us understand more about the raw data. But we can use the stem plot to contextualize where a particular number fits in with the rest of the distribution. If we take a single measurement from the big group, let's say 25.1, where it fits in with our stem plot gives us a sense whether a particular soldier's foot is on the larger or smaller side, something that would be harder to determine just looking at the raw numbers. Here's another data set where a stem plot can help us visualize the numbers. Fuel economy info for Toyota's vehicle line. We arrange the miles per gallon numbers in order, this time from highest at the top to lowest at the bottom. Then we build our stem. Since the MPG data are all whole numbers, we'll use the tens place as the stem, and the leaves will be the ones place. Include stems even for numbers that don't have leaves to go with them. Take a look at the overall pattern. Most of the MPGs are clustered here at the lower end. We can expand the stem to change the resolution of our picture. If we zoom in on the data, will it help us understand the numbers even better? Let's break each stem into two, so the low-digit leaves 0, 1, 2, 3, 4 are on a different stem than the high-digit leaves 5, 6, 7, 8, 9. We've got outliers again, but this time an explanation is obvious. The high numbers are due to the super fuel-efficient hybrid vehicles Toyota makes. Stem plots can be used to compare two different data sets as well. Say we wanted to compare Toyota's 2012 numbers with those from their 1984 line. We can make a back-to-back stem plot to see how mileage numbers have changed over the decades. Use the same stem for two separate sets of leaves. Interestingly, today we have more vehicles way down at the low end, and a few more up at the high end. These extremes are easy to explain when you think about what you see on the roads these days. Modern car buyers are interested in the not-so-fuel-efficient SUVs and trucks, as well as the uber-efficient hybrids. So you can see how stem plots start to wrangle some meaning out of the disorder of raw data. They are useful for visualizing the shape of your data's distribution and figuring out how frequently particular data classes pop up in your sea of numbers. And stem plots are just the first step. There are plenty of other statistical ways to visualize data. Stay tuned. I'm Pardeep Subedi for Against All Odds.
So a couple interesting things that are in that that we did not really talk about before. I really appreciated the fact that when they were looking at the soldiers' data and they were just put, they had a new person come in, they measured his foot was 25.1. They could compare that to the small 7-leaf plot to see where he was, right? So was he fall on the small side or the large side? The other thing then was with the foot lengths, remember that it was 25.1, which then turned out to be in the stem 25, and then the leaf was 1. So our stem was our whole number, and the leaf was the tenths place. So that's a different thing that we didn't see with our data for the baseball data. Then we did see the back-to-back with the fuel economy, but the thing they did with the fuel economy, which was interesting, was then they spread it out. So you can have, for example, the low 20s and the high 20s. So 20, 21, 22, 23, 24 would be in the first part of your stem. And then 25, 26, 27, 28, 29 would be in the second part of your stem. Both of those skills or strategies are something that are important when you're looking at data. Remember that your leaf can only be a single number, and that forces you then to figure out what your leaf is going to be, what the stem's going to be. Also, there was times where the stem went least to greatest or greatest to least, you flipped it with how it made sense, okay, with looking at the data. All right, so I think, let's see, here we go. Cool fact. So I try to put in some of these every once in a while. Once again, numbers have been around for a long, long time, since the Egyptians and the Greeks and the Aztecs. But 7-leaf plots are relatively new, actually. They were developed by a statistician named John Tukey in 1977, which I know feels like a long time for you, but I was 5 when that occurred. Woo! Go 5-year-olds. I was in kindergarten in Hilton Elementary School in the Village. Okay. Turn the page. Beep. All right. So the pain of a 7-leaf plot is actually making the 7-leaf plot. I tried to do a little bit of modifying of my previous notes to make it a little bit easier, but the idea is that you have to practice it to make sure you know how to do it. A couple things up here I bulleted. If you're doing it without sorting the data using some sort of calculator, you actually have to do your stem and leaf plot twice, right? The first is for sorting, and then the second is for organizing those leaves. And remember, the leaves go from least to greatest from the stem out, okay? And so if you're going in the opposite side, the smallest numbers are always closest to the stem, and you're moving away from the stem on either side. And there it goes. The stem can go from low to high or high to low, and then it's essential to include your title and a key. So when you say title, tick, tick, label, 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 the key is the thing that typically most students forget, okay? But remember, it's kind of like, how do I read this? Is this the tens place, the hundreds place? Is it the ones place? You need to let somebody know. All right, so here is an example, and of course, these numbers are not realistic to today's cell phone behavior, but it says the following are numbers of text messages sent last week by the cellular phones used on one floor of a college dormitory. I feel like this would just be sent in 1 hour. Display the data in a 7-leaf plot. What can you conclude? All right, so we're just going to go ahead and kind of start the unordered one, and then I have the finished one ready for you. Okay, so we aren't wasting our time completely on that. But just when we have this massive amount of data, a couple of things you can do, and I did not talk about this last time, so this is an important idea to think about, is you kind of want to break up the data into chunks so it's easier to read. Sometimes I'll just put vertical lines through the data to make sure that my eyes track properly through the list as I'm doing it. Okay, these vertical lines just literally help yourself read the data. And I would probably read the data, like as I'm putting it in, I would read column 1, then go to column 2, then go to, you know what I mean? I do that. And that's how I would stay on track putting my data in. The next thing you always want to do is look for your minimum number and your maximum number. So let's take a quick look. What is our lowest number of text messages? I see a 78. Is there something lower than 78?
No.
Okay, 78. What's our highest number? There's a 150? 159. Okay. And actually, I probably could have looked at the answer to figure that out. So, which, you know, why would I do that? So then when you're looking to figure out how to do it, you can only have one place value. So there is what you have for your stem and your leaf. Your stem has to go from 7 to 15. And then I typically, if there's not a reason to, I do it like this is I do lowest to highest, because then I can turn it and it looks like my histogram. So if there's not a particular reason to have it the other way, that's the way I'll do it. So let's just go ahead and put our stem in, and we'll do like the first 8 leads, and then we'll look at what we have. Okay, it's just that way when you have to do a full one, you understand the process. So we start off with our stem, 7, 8, 9, 10, 11, 12, 13, 14, 15. And then I'm going to back out and I'm going to look at my data. Okay, so here we go. So reading down my first column, I have 155. $126, $109, and $132. And then doing my second column, I have 59, 18, 19, and 33. And so to take the time to do this one is pretty laborsome. The other thing is when you're physically writing numbers, you might not space them out perfectly, right? And so it's nice to have technology or grid to help you make your box and whisker, to help make your stem and leaf plot, my bad, so you can really see the shape. So once again, they just picked a piece of data to use as a key, so don't forget that. And then our title, number of text messages sent, good enough. And the nice thing we can see right now is that, yes, there is clearly some sort of shape up here. We have, you know, I don't want to say it's a maximum. It's a peak, right? A peak in our data. I would assume that somewhere in here in the 120s might be our middle, right? I am not calculating that center at all, but I can eyeball it. We have a gap here in the 80s and 90s. Maybe that person that's there at the beginning still had to do, what was it called? It was like a T9 phone or something. You had to press, it used the keys on the telephone. So you would have to, if you wanted the letter B, you would hit the 1 key twice. Because it goes A, B, C on the 1. And then D, right? So you would have to, I think it was called T9. I can't remember. But that was my first cell phone that could text. That's what it did. It was a pain in the butt. You got really good at it. And the nice thing is you didn't have to look at your phone to do it at all. Right? You could feel your keyboard. At any rate, so the next thing we could say is, say I met somebody on the dorm floor and they had 140 text messages for the week. I would say, oh, they are kind of above average. Right? So you can estimate a single person's behavior based on looking at this small data set. So remember that this is a sample, right? We're looking at sample of college kids on one floor. Okay. All right. Are you ready to turn the page? Beep. Okay. So now we're going to go through and we're going to use Oh no, John, I think I did. Wait, I think I might have done all of this. Oh, we're going to expand it. So now this is the process of expanding. Okay. So here you can see in the 110s and the 120s, there's a lot going on. So if there are too many leaves in a row, it is helpful to have 2 branches for each stem value. And we're going to do the 0 to 4 and the 5 to 9. This is called expanding to see what's going on. All right, so even starting at your lowest, you don't necessarily have to do the low 70s, but you can. So we're going to go ahead and start here at the top, and we're going to have 2 7s, 2 8s, 2 9s, 2 10s, and so on. And since we have an ordered stem and leaf plot, expanding it is not difficult at all. But you kind of want to remember where you started. So this first 7 is for 70 through 74. So our 78 is going to go with the second 7. We go down to the 10. The first 10 is not going to have anything, right? But 105, 8, 9, 9, 9 is going to go here. And then you can kind of go ahead and look at the 11s and see where you're going to split it. It's going to be split between the 4 and the 6, right? So the first one is going to be 112, 12, 12, 13, 14. But then the next one is going to be that 6, 7, 8, 8, 8, 9, 9, 9. Does anybody need a visit? Does this make sense what we're doing? The 5s go on the next one. So it's kind of like rounding rules, right? 5, 5, 7, 8. Then we have 5 and 9. So we spend so much time making our simile plot that this is where sometimes I like to set up that key and the title beforehand. So our title would be the same exact thing, number of text messages sent. We could use the exact same key as well. So those things don't have to change. Bless you. Okay, so building up our skill of interpretation does take a little bit of time, and what we do tend to do is talk about center and spread. Right now, though, we're just going to focus on center, and we're not going to calculate the mean or the median, but now we can certainly say that it feels kind of like these 3, right, or maybe even these 4 rows appear to be the center, right? Somewhere in there. So in that, we can say a typical student, so the word typical, sends between, and then we decided that 115 was our lower bound to 134 text messages. So we're just kind of looking at that center. We're not too concerned about an outlier at this point, right? It's not, number of text messages is not significant enough of a concern to worry about outliers on either end, except maybe on the high end, right? If someone had 1,000 text messages in a week, you might be wondering what's going on in their life, right? At least for this data set. All right, so there's another example spread out, so you now have seen it expanded. So go ahead and turn the page. We have one more data set to play with. And this is the one that's going to have decimals in it. All right. So what can we do? Something with non-integers, and the answer is yes. We just need to make sure that only one place value is the leaf. So for example, if we did something like we had numbers like 20 or 2 point, if I was doing the cost of something, $2.97, I could have 2.9 in my leaf, and maybe 2.8 would be the next thing in my leaf, right? And then I could have the 7 as the hundredths place. So the deal with the 7 leaf is that you're just restricted to the leaf being a single digit. That's the restriction. All right. So with this, we have data about the price in cents per pound. So we're talking about fractions of pennies now for apples for 28 farmers. Okay, so I have all of these things set up so we can do disorganized, organized, and then spread out. Okay? All right, so let's first of all just get our max and our min. What's our lowest price? What's our highest price? Okay, so we have 16.4. Good. And then what's our maximum? See a 19.6. Oh, there's a 20.8. Anything higher than that? Nope. Okay. So that means we need 16, 17, 18, 19, and 20. Once again, to kind of help me stay organized, I might draw these vertical lines here to help me read the data more carefully. All right. So go ahead and just start sorting in your leaves disorganized. You're just getting them in there. You're not organizing. So I'm just reading. Make sense? Nancy, does this make sense what we're doing? Okay. Okay, so you have a 20 on there. Down at the bottom under your 19, you need a 20. Okay. Okay, so this is the deal. So the stem can be as long as, as big of a number as we need it to be. But you can only have one digit as the leaves. So to represent 19.2, I'm going to go to the 19 line and just put a 2 here. Okay. So 20.1, I'm going to go to the 20 and put a 1. And then I'm going to put a 5 in the 19. Right? I'm going to go to the 18 and put a 6. Okay, so now just pause for a second. So the way we read it, we would have a key, and it would say 19 bar 2 means 19.2. So now I know that this is 19.2, 19.5, 19. Whatever number comes down. Okay, so our first job is literally just to get these text placed in here. It's going to be all messy. Does that make sense if you do that part? Okay, do that part. Okay. Okay, so if you have it down, now you can organize it next if you're ready to organize. All right, does this make sense what we're doing? Okay, so up here, you put the 2, these ones, now you got to keep going. At 19, you put a 6. At 19, you put a 0. At 18, you put a 4, right? So for each of these, there's going to be a leaf. Okay? this first one was for sorting. Can someone check my work? Is mine right? Good. Okay, great. So then this is where we have that perfect example of it's really too clumpy to understand what's going on, right? So we're going to expand it. So then you would go up here and go 16, 16, 17, 17, 18, 18, and so on. All right. The things to remember then is at the end or as you're doing this, you need to put a title. So apple prices, cents per pound. And you need to put a key. So even if I just have these on here down at the bottom, because that's where I have room maybe, I would put a key. I'd write the word key. Oh, and I'm sorry, I have the 8 in the wrong spot. Don't yell at me. Blue. 8 goes here. My key is 16.8 or 16 bar 8 means or equals 16.8 cents per pound. So don't forget that key, don't forget that title. All right, so I know I've lost you. It was a long lecture with a video, but basically, what are some of our advantages to a stem plot? What can it do for us?
Reading data easier.
Say it one more time, a little louder.
Make reading data easier.
Okay, so it can organize our data. And we also get to therefore keep the raw data, right? Can we see shape and center pretty easily? Yeah, you can see. You can also see if there's a possible outlier. But I would totally agree that the disadvantage is you wouldn't want to do it for a large set unless you had, large sets, it doesn't work for huge sets of data. And with not using technology or not having it already sorted, it is kind of obnoxious to make, right? Do we agree that this is obnoxious? So the deal is this. You need to know how to make a stem and leaf because you have to know how to read a stem and leaf. Does that make sense to everybody? Okay. So I have a homework assignment for you. Why don't we do this? The front we'll do as a warm-up tomorrow in class. Does that make sense? So do you have to do the front tonight?
No.
No. But do you have to do the back?
Yeah.
Yes. On the back, there's 2 stem and leaves to read and 2 dot plots to read. Dot plots are pretty easy, right? It's just every dot represents a thing of data. It's a matching game. Description, match. So you have 4 matching questions for homework. Can you do it?
Yeah.
That's easy. All right. And you have plenty of time to clean up. So 1, 2, 3. Merry Christmas. So just a question on the back.